We have to do our review problem, right? Okay, so what is the area for the triangle with vertices at minus 2, 7, 1, 4, and 6, 5? All right. Do we have an answer? Did somebody figure this out? I see a hand over there. Think it's 6. Okay. I can't remember for sure. Any other answers? 10? 9? Anyone want 8 or 7? Anyone? Anyone? Okay, so we had answers of 6, 9, and 10. Now I don't know. Okay, let's see. Well, I'm pretty sure it's one of them. Now, what's the clue of what to do? What's the key idea that we see? Or something like says, we've seen this before. Area of what? Triangle. Do we know anything that does areas of triangles? Cross. So it's like, we've seen areas of triangles before, so we know that the area of a triangle is 1/2 the magnitude of u cross v. And life seems good. But now I see that cross product. What's true about cross products? Sine. Yes. What else? There's something about cross products. It only works in 3 dimensions. How many dimensions are we looking at? We're looking at 2. Does that mean that we must abandon the cross product? It does not. Okay, why not? I think somebody said it. Add a 0. You see, true fact, the xy plane, this is our 2D xy plane, sits inside 3D. So, what does that say? Well, it says that if you have a 2-dimensional problem, you can use 3-dimensional tools. The only thing you have to do is add a 0. So we'll just add zeros. Now you just have to be consistent. So negative 2, 7, 0, 1, 4, 0, and 6, 5, 0. All right. So now we have 3 points in 3 dimensions. We can take the cross product. Well, we can't take a cross product yet because what do we need to take a cross product? Vectors. We have points. So what do we do? So we have these 3 points here in the xy plane sitting inside 3-dimensional space. What do? Yeah, subtraction. Retreat says, hey, you're looking at change. Make the vectors. And so we pick a vertex, doesn't really matter which one. We're going to go out to the other 2. So let's suppose we'll start from negative 2, 7, 0. What's the change going from negative 2 to 1? 3. The change from 7 to 4? Negative 3. Change from 0 to 0? 0. Okay, now again we'll go from negative 2, 7, 0 to 6, 5, 0. From negative 2 to 6, what's the change? 8. From 7 to 5? Negative 2. 0 to 0? 0. Now, I should pause and say, you might ask a question, does it matter which one I pick? Which vertex I pick to be the important vertex? For the final answer, it won't matter. For the intermediate work, it might look different. But it won't make the intermediate work necessarily easier or harder. So don't overthink it. Just pick a vertex and go with it. All right, and it also doesn't matter which one is u and which one is v. So we'll take the cross product, 3, negative 3, 0, cross 8, negative 2, 0. Okay, set up our 3 by 3 matrix. Now, the good news is we like zeros. So we actually appreciate the number of zeros that we see here. We start taking our diagonals. I times negative 3 times 0. I times negative 3 times 0? 0. J times 0 times 8? 0. Nice. K times 3 times minus 2? Minus 6k. All right, those are our diagonals in one direction. Now the other way. 8 times minus 3 times k? So we're going to be negative 24, and then we subtract it. All right, because it's the other direction. Negative 2 times 0 times I? 0i. And we subtract that. 0 times 3 times j? 0. And we subtract it. Which also, so negative 6 minus minus, 2 minuses make a positive. So this becomes 18k. Now, we have to take the magnitude of this vector. So we have to take 1/2 times the magnitude of 18k. Well, what is the magnitude of 18k? 18. So you get 1/2 times 18, which is 9. Aha! And someone did say 9. Woohoo! All right. So there we go. There we go. Any questions on this one? This one can be a little bit trickier because there's not really a way to sort of check your final answer, right? There's a lot of answers that look pretty tempting. You know, sometimes you can say, if I don't know how to solve the problem, I can just say, what are the solutions, and plug it back in to see which ones work. Those are sometimes a little bit simpler when it comes to multiple choice. This one, it's a little bit more subtle. They do that sometimes. All right, so, thought for the day. Steve Jobs, no relation. Not all Steves are related to each other. And said the following: simple can be harder than complex. You have to work hard to get your thinking clean to make it simple. But it's worth it in the end. Because once you get there, you can move mountains. And today, our goal is flat things. Simple things. Because it's like, what could be harder than a flat thing? Or what could be simpler than a flat thing, I should say. But it's hard to get it down. And you have to think about it. I like math. I'm biased. And for me, I think math is beautiful because it's simple. A lot of times people think it's complicated and that there's all these rules. But once you dig into it, you'll see that there's just clean ideas underneath it. And I hope you get there. Because when you do, it becomes a lot more fun. All right, so anyways, what are we doing? Today, we are in our flat phase. We're going to talk about one-dimensional flat things. We call these lines. And we'll talk about ways to represent lines. There's a vector format and a parametric format. And lines are somewhat familiar with us already, so hopefully it won't be too surprising. And then we're going to go to our other flat thing, which is a plane. And here, I should say all this is we're phrasing everything in terms of 3 dimensions. And so for planes, it turns out these have the equations ax plus by plus cz equals d. And we'll talk about what it takes to make a plane. So you notice up here we said a point and a direction vector gives a line. Well, you need to know where you start. You need to know which way the line goes. For planes, it's a little bit more interesting. You need a point and what's called a normal vector, and we'll talk about that. And the other thing is we're going to talk about distance. Distance from a point to a line and distance from a point to a plane. And I want to note that if you're following along in your formula sheet, these formulas for distance are in your formula sheet. So this little symbol with a dot and a line is supposed to represent the distance between a point and a line. And what looks like a dot and a little plane, that's the distance between a point and a plane. So now our formula sheet continues to grow. New things to be learned. And we'll show where these formulas come from. And no surprise, they're going to involve cross product and dot product. And I know that doesn't look like a dot product, but we'll get there. We'll get there. All right, so let's start with the line. Our one-dimensional flat thing. So we're already fairly comfortable with the idea of lines, I hope, by this point. I mean, Calc 1, we build off of this idea of a tangent line, so we spend a lot of time talking about lines. But in there, we talk about, well, you need a point, and you need a slope, or rate of change. But really what that slope is telling you is it's telling you the direction of the line. So in 3 dimensions, we want to do something similar. What do you need? A point, because you have to know where the line is in space. You have to locate it. And then there has to be a direction vector for that line, which tells you the direction that the line goes. And how do you get that? Well, one way to get it is if you know 2 points. Because if I know 2 points, what can I do? Well, you can do the following. Let's suppose I have a line here, and I've marked, here's an initial point, then here is an arbitrary point. Well, let's just call it x, y, z. And we'll get into this in a second why I have this marked down. But how do I find the direction vector? Well, if I pick any 2 points, what's true about the vector connecting this pair of points, and the direction vector? They're parallel. So every 2 distinct points will form something parallel to the direction vector. And the direction vector isn't distinct by any means. You can always scale it by any non-zero amount. So it's not hard to find direction vectors if you have points. And so you just take the difference. So x minus x0, y minus y0, and z minus z0. Boom, you have your direction vector. The other thing that will often happen is to say, well, if you can say that your line has to be perpendicular to 2 things, then you take a cross product. So anytime you get this notion of perpendicularness coming into play, you should think, cross product. That's how you form new directions. All right, so how do we describe lines? Well, we already mentioned that if we take the difference of 2 points, we get things which are parallel. To be parallel means you differ by a constant multiple. So this vector x minus x naught, y minus y naught, z minus z naught is some multiple of the vector ABC. So we get this relationship. Now we just split. So this can be written as x, y, z, subtract x naught, y naught, z naught, and move the point around. So you get x, y, z equals x naught, y naught, z naught plus t, a, b, c. And here we're a little bit careful because we know this is a vector, but we're going to interpret it as a point. This is one of the things that we often do. For convenience, we can always think of, they're saying, look, let's take a vector and we just take the end of the vector and nail it down at the origin and just say, where is the arrow pointing to? So we can oftentimes interchange a point and a vector. We just have to make sure we're comfortable with that switch. So for any point on the line, you start at your initial point and you travel some direction. Well, you travel in the direction vector some amount. So every point can be described that way. So that's the vector description. I tend to prefer the other way to describe lines, which is parametric. So if you've seen something where it says parametric curve or parametrized curve, the parametric form, the parameter is almost always using t. It's just saying we're going to let t vary. It's something that can move around. We have a choice we can make for t. So as we pick different values of t, what will happen is we'll actually get different points. So as t changes, you plot lots of different points on the line, and then the collection of points that you form is the line. So that's what we mean by parameterized curve. Now, what do? We just compare the slots. we have the first slot says x is equal to x naught and then plus a times t. Compare the second slot, y is equal to y naught plus b times t. Z is equal to z naught plus c times t. And we have this set of equations. And we can say, aha, you can read off the point. You look at the numbers without the t's. And you can read off the direction vector, because those are your coefficients of your t's. Vice versa, if I have my point and I have my direction vector, I just have to fill these slots in, and life is good. Now, one word of warning up here in this corner. There is a sort of a bias away from lines when they write these on exams, because it turns out you can write the same line in many different ways. So if you're working on a problem that says find this line, and you're doing it with a friend, the two of you can come up with very different looking answers for the exact same line. Well, why can it look so different? How many choices do you have for your point? Infinitely many. Any point on the line is a valid choice for a point when you're describing it with an equation. How many options do you have for your direction vector? It's still infinitely many, because you can scale it by any constant that's not 0. You can multiply by negatives. That's perfectly fine. So it is very possible that two people can write the same line that looks different initially. Then you just have to sort of say, okay, well, let's just check, are the direction vectors multiple of each other? All right, does your point fit on my line? Does my point fit on your line? And then you can be like, oh, yeah, we got the same line. So that's just something to be aware of. All right, let's do a small question. You can tell it's a small question because there's not a lot of space here. All right. Find a parametric form for the line going through 315 and 249. So, in other words, we have 2 points in 3-dimensional space. So, we can draw a picture. It has to be a tiny picture, but we have 315. Here's a point, and here's point 249. And once you have 2 points, you just say, look, there's a unique, straight, one-dimensional thing that goes between those 2 points. That's your line. That's what we're trying to find. And we're told parametric form. So when I'm thinking about making a line, I say, well, I need a list of things. I need a point on the line. Do I have one of those? Yeah. I have choices. Does it matter which one I pick? No. All right, let's just say we'll make the first one our point. So here we go. We're halfway done. And on a side note, never underestimate the power of partial credit. Sometimes on problems where it'll be like, hey, find the equation for the line. You say, well, I don't know how to find the direction vector. Oh, I know how to find the point. Write that down. You'll get some credit for that. And every point matters. But of course, we want to get all the points. Okay, so what else do we need to make our line? The direction vector. So how do we get it? Well, we have 2 points. So what can we do with those 2 points? Yeah. Make the vector going in between them, looking at how you changed. So from 315 to 249, if we look at that vector, so we'll look at, call our vector v. 3 to 2, our change, -1. 1 to 4, 3. 5 to 9, 4. So -1, 3, 4, and our point, I'll write it down here for reference, 3, 1, 5. Now, I do the following. X equals, Y equals, Z equals. And I say, okay, first, we're going to focus on the point. That's our first set of numbers. And so we write those down. 3, 1, 5. All right. So those are our numbers. Then I say, okay, that's my coming from the point. Now I need to get the coefficients of t, and that's going to come from the vector. Negative 1, 3, 4. So we say, okay, so this will be plus a negative 1 times t, which we usually write as negative t. A 3 times t, so plus 3 times t, and a 4 times t. 4 times t. So, from taking our direction vector, we've got those numbers. And what do we do now? Put a box around it. Because we're done. That's the answer. All right. Any questions on lines? Well, here's a quick question for you. Find the line which perpendicularly intersects the following two lines. X is 3 plus t, y is 2 minus 2t, z is 5 plus 3t, x is 3 plus 4 tau, y is 2 plus tau, z is 5 minus tau. The reason this uses t's versus this using tau's, different lines, I just want to emphasize they're having different parameters. So t and tau can behave independently of each other. So what the time choice, the parameter choice for one, is different from the parameter choice for the other. Okay, I claim these intersect. Is there a reason why we can believe that they intersect? How do we know they have the same point? Yeah, they share a point. Sometimes it's not so obvious. And when it's not obvious, you have to actually figure it out by choosing the right t and tau. We already made the comment, hey, these intersect like the problem says it does. So that takes care of our point. So yay us. What do we do to find the direction? Yeah. What's the clue cross product is involved? As soon as you see perpendicularly, you're like, oh, I've got to be perpendicular. Now, I could have phrased this problem slightly better, perpendicular to both lines simultaneously. So, well, what's the direction vector for the first line? 1, negative 2, 3. For the second line? 4, 1, negative 1. So you get I, J, K, 1, negative 2, 3, 4, 1, negative 1. If you got to this point, you're doing great. You're on track. Now, if you go a little bit further, even better. But we were pushing you a little bit for time. Did somebody work this out? Do we have an answer? Or do we want to? Yes? Negative 113.9. Now, I asked for an answer from the audience. If I was a little bit nervous, what can I do with this answer? Check it with dot products, right? Negative 1 minus 26, that makes minus 27, plus 27 is 0. Negative 4 plus 13 minus 9 makes 0. So this is good. This is good. Now, by the way, don't check with your neighbor during the exam. That's not a strategy that we recommend. But that's all right. Now, that's our direction. And lo and behold, we have point plus direction. We just put it together. So we have the same 3, 2, 5. And then we say, okay, plus a minus 1 times t, so minus t, a 13t, and a 9t. So these coefficients, minus 1, 13, 9, coming from the direction vector. All right. Now, before we leave lines, let's talk about the distance to line formula. And because it's on the formula sheet, I don't want to stress too much about like, you got to remember this, but I want to explain why it works. So here's the idea. You have a distance from a point Q, and there's a line which has point P, and there's a direction vector U on that line. The claim is it's the magnitude of the cross product, PQ cross U, divided by the magnitude of U. Now, it's not obvious that cross product should have anything to do with this. But think of the picture. So, what do we want? Well, we want the distance. And whenever we think of distance, you should always think of, if I go from the point Q to wherever I'm trying to get closest to, there's this right angle involved. Right angle is an indication of optimization. So we say, okay, what we can do is make a little triangle. One of our sides is the part from P to Q. One of our sides is the distance, and the other side is the line. Now we can find the distance from P to Q very explicitly because we can find the vector P to Q and talk about its length. We're after the distance here, and this side is just not going to be easy to nail down, the side with the line. We're not going to be able to nail that length down. But what we can nail down is this angle in the corner, because that's the angle between the direction vector and the line from P to Q. So we say, okay, we have an angle. We understand the hypotenuse. We want the opposite. What relates opposite and hypotenuse to an angle in a right triangle? Sine. And if we see sine, what do we think? Cross. So the distance turns out to be magnitude of PQ sine theta. We're like, let's make this into a cross product. Because theta involves U and PQ, I need to add a magnitude of U. But if I add it upstairs, I need to add it downstairs. Now the upstairs is a cross product, and then the downstairs is this extra magnitude of U. And that's the derivation. So finding a distance to a line is fairly straightforward. Now, suppose, theoretically, one were asked the question, you have two exactly parallel lines. So they have the same direction vector. How would you find the distance between two lines which were exactly parallel, had the same direction vector?
Would you use a point from both lines?
Well, we wouldn't necessarily use a point from both lines. What you can say is, if I know the distance from this point to this line, then I'm good to go. Because that's the same as the distance from this point down to this line. Because these are exactly equal. Now this says what? Reduce to an earlier problem. In other words, I can say, instead of worrying about the whole line, I just pick a point. But this critically relies on the lines being exactly parallel. The direction vectors have to be multiples of each other. What if they're not multiples of each other? That gets interesting. We need more things to do that. But I just want to point that out, that there's always this idea of, hey, you can reduce to a simpler problem. All right. So, our other thing we need to talk about, planes. These are our 2D flat thing. So think of a plane like a sheet of paper. We've talked about planes before, like XY plane, XZ plane, YZ plane. But now, they're not just, right there on the floor. We can pick it up. We can tilt it one way or the other. And we have lots of ways we can maneuver around. But the important thing is it's a two-dimensional thing, and it stays flat. Now, how do we describe a plane? What do we need? Well, we definitely need to nail it down in space somewhere, so you need a point on the plane. And then the question is, well, what's the direction? Well, that's a little bit of a technical issue, right? Because let's suppose we're just talking about the XY plane, so we're talking about the floor. How many different directions can you go in the XY plane? Yes, lots of them, right? You can go just purely in x, just purely in y, some combination of x and y. So there's infinitely many directions inside the plane. That's not a good number. We want to somehow get that smaller. But now we use the advantage that we're in three-dimensional space. And 3 equals 2 plus 1. We've mentioned this before. So we say, okay, look, that plane is 2 dimensions. So there's one thing, exactly one direction, perpendicular to it. So when we think about a plane, we're going to use the normal vector. And when you see the word normal, you should say that means perpendicular. So a normal vector is perpendicular to all the vectors in the plane. And here, this is not an x, by the way. This is a cross. Because you want it to be perpendicular to everything in the plane, if you want to find the normal vector, one of the most common things to do is say, okay, let's find our two vectors in the plane, cross product, and that will be our normal vector. So again, pictorially, there's lots and lots of directions we could go inside the plane, but there's a unique direction perpendicular to the plane up to a constant multiple. All right, so now that we have this idea that we have a normal vector, so here this ABC is representing our normal vector, and it's perpendicular to anything in the plane. Well, suppose I look at a very particular vector. So I have my initial point, x naught, y naught, z naught, and now here's some arbitrary point in the plane, x, y, z. I take the vector connecting those 2 points, x minus x naught, y minus y naught, z minus z naught. That vector is in the plane. What's true about a normal vector compared to a vector in the plane? Dot product is 0 because they're perpendicular. So we take their dot product and set it equal to 0, and you get a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. Well, you do some rearranging. You can distribute the terms through and move things around. You get ax plus by plus cz equals a bunch of numbers. You say, okay, just collapse those bunch of numbers. We call it d. So the generic form for a plane is ax plus by plus cz equals d. That expression is unique up to multiplying both sides by a constant. So there's a little bit of a preference for questions which ask for planes when you're grading, because it's easier to identify correct planes. One thing to point out, if I have a plane, I can read off the normal vector. I just have to read off what are my coefficients of x, y, z. Make sure your x, y, z are all on the same side, but then just say, okay, hey, I can read those numbers. All right. So how do you find your plane? 90% of the work is going to be trying to find your normal vector. So you have to think about what is the geometry of the problem telling you. Sometimes it's more straightforward. Sometimes it's more subtle. Sometimes it's really subtle. But think of the geometry of the problem and think about how you can get that normal vector. And start thinking about, well, if you have information, you have vectors, how do those vectors relate to your normal vector? And oftentimes you'll say, oh, they need to be perpendicular. And you start saying, okay, I'm on my way to a cross product. So once you have your vector ABC, you're basically done. That says I have ax plus by plus cz equals something. And then the age-old question, what's in the box? What's in the box? Well, okay, so how do you plug in and get what's in the box? What do you need to plug in here to get what's in the box? You have ABC. What else do you have that we haven't used yet? Yeah, you have some point. And plug that point in, that tells you what goes in the box. And you're done. You have your plane. Okay, so quick problem, because again, not a lot of space. Find the plane perpendicular to the line x equals 3 plus t, y equals 5 minus 3t, z equals 6 plus t, passing through the point 1, 2, 9. All right, so there is a line in space. Okay, here's our line. There's a point. It's probably not on the line. And now we want to have the plane that contains that point and is also perpendicular to the line. How do we do that? So remember, we're looking for normal vector. Is there an easy way for us to grab a normal vector here? The what? Well, there's not a distance here. Okay, slope of the line, but here we don't call it slope. Yeah, the direction vector of the line. Now, which one of these two is the direction vector? The 3, 5, 6 or the 2, minus 3, 1? How do you know it's the 2, minus 3, 1? What's special about that? Has the t. The part where the t is, that's the part which is the direction vector. So we say, hey, we know the direction vector of this line, at least one of them, is 2, minus 3, 1. That line is perpendicular to the plane that we're after. So what's the normal vector to our plane? Yep.
2, negative 3, 1.
Yes! Yes! It's perpendicular already. We don't they gave it to us on a silver platter. We're not going to be like, no, we are not taking your free gifts. We want to struggle. No, we're not going to do that at all. We know that this line is perpendicular. So the direction of this line is perpendicular. So we can use our normal vector is 2, negative 3, 1. So we're almost done. So our plane looks like 2x minus 3y plus z equals something. All right, how do we get our something? All right, which do we plug in? The 3, 5, 6, the 2, negative 3, 1, or this 1, 2, 9 that we haven't talked about yet? The 1, 2, 9 that we haven't talked about yet. This 3, 5, 6 will not come into play in this solution. Now, it's not immediately obvious from the beginning, but it's okay. So we plug in 2 times 1 minus 3 times 2 plus 9. Well, that becomes 2 minus 6 plus 9, which becomes a number. Yeah, that's true. It is a number. Anyone know what number it is? 5. Oh, go. Thank goodness. Phew. So 2x minus 3y plus z equals 5. And that's the problem. We're done. We're done. All right, we've got about 5 minutes left. Let me jump to this one. We talked about distance to line. Oh, any questions about planes? I don't want to make you nervous, but I will tell you, a non-trivial number of people struggle with plane problems. That is to say, there's subtleties. So the important thing is think geometrically, think about your normal. Focus on the normal. You can almost always get what you need. Okay, distance to plane. So, again, this is from the formula sheet. So you don't have to memorize this, but why does it work? So you have a point x naught, y naught, z naught. You have a plane ax plus by plus cz equals d. The claim is you get ax naught plus by naught plus cz naught minus d over the square root of a squared plus b squared plus c squared. If you look at the top here, it's almost like, oh, plug the point in and just say, how close were you to the right-hand side? Because that's what you're doing. Now, how close is it when you plug in your x naught, y naught, z naught the two sides. And then the downstairs says, oh, make sure you scale by the size of your normal vector. Why does this work? Well, I have my plane. Here's the point I'm trying to get close to. And I can take my normal vector and I can assume my normal vector is just right, because I'm allowed to move my normal vector. Right? We have freedom. If I have a vector, I can move it to a more convenient location. So I'm going to move it so that I'm coming perpendicularly off the plane, and that if I were to keep going in that direction, I'd hit the point I'm interested in. In the meantime, I'm going to make up some unknown point that I don't know, because I haven't figured out what that is, that's in the plane. I'll call it P. X1, Y1, Z1. You might say, that's not part of the answer. It's not, but we'll get there. And I draw a triangle. Not any triangle, the right triangle. The right kind of triangle. And here's the great aha. This this angle is the angle between P to Q and N. Now, what do we want to know? We want to know the length of the adjacent side of this triangle. That's the distance. And we can find the hypotenuse. What relates adjacent and hypotenuse? Cosine. And when we see cosine, we think dot. So the distance is the magnitude of PQ times the cosine theta. You need to toss in some absolute values because, well, it could be a negative value for cosine. All right. Well, it's like so close to a dot product. Throw in the magnitude of n's, and we got a dot product. And so now we say, it's this normal vector dot PQ over n. You're like, okay, but can you rewrite that? Well, carry out the dot product just like we did when we derived the formula for the plane. You get ax naught plus by naught plus cz naught minus ax1 plus by1 plus cz1. But because x1, y1, z1 is a point in the plane, and every point in the plane satisfies ax plus by plus cz equals d, this last piece becomes the d. So you get ax naught plus by naught plus cz naught minus d over the size of your normal vector.